Let's look at the next question. This question is from the topic random variables. He said the random variables y is equal to integral minus infinite to infinite w of t into phi of t dt, where phi of t is 1 between 5 to 7 and 0 otherwise, and w2 of t the real white Gaussian noise process with two-sided power spectral density 3 watts per hertz for all f. The variance of f is. Now, how to solve this problem? Let's write the given data. In the question, he said y is equal to integral minus infinite to infinite phi of t into w of t dt, where phi of t is 1 between 5 to 7. This is phi of t, and he is asking us to calculate where w of t is a white Gaussian noise having the constant power spectral density 3 watts per hertz. 3 watts per hertz. So this can be written as SW of f. Now he is asking us to calculate the variance of y. We know that variance of y expression is nothing but expectation of y square minus expectation of y whole square. Now let's calculate the expectation of y. Expectation of y is nothing but integral minus infinite to infinite. Now expectation being a linear operator, I can take inside the integration so that this becomes expectation of w of t, as phi of t is constant between 5 to 7, phi of t dt. Now power spectral density is given here. Now we must calculate the expectation value, and from the power spectral density, can we calculate the expectation value? Expectation value, in other words, is also known as DC value, or this is also known as average value. Can we find out the DC value from power spectral density? For that, I'll take up one signal here. See, suppose if I have AC cos 2 pi fct. Now, if I want to calculate the power spectral density for this one, first of all, what I'll do is I'll calculate what is known as autocorrelation function. So, which is given by AC square by 2 cos 2 pi fc tau. And we know that autocorrelation function and power spectral density, they form a Fourier transform pair. Means if I want to calculate the power spectral density, simply calculate the Fourier transform. Fourier transform of cos means what? Two impulses will come, one at fc, the other at minus fc. So this is the power spectral density, each of area having AC square by 4. Now you can say one thing, that this is power spectral density. From the power spectral density, we can calculate the power also. So total area under power spectral density gives power. Here power in this one signal is AC square by 2. AC square by 2. If I calculate the total area, AC square by 4 plus AC square by 4 comes to be AC square by 2. So I can calculate the power from power spectral density. Suppose if I take 2 plus AC cos 2 pi fct, what will happen to the power spectral density? Here 2 is there, a DC signal is there, DC plus AC cos 2 pi fct, and we know that if you calculate the autocorrelation function for the DC 2, it will be 4 plus for this one AC cos 2 pi fct is AC square by 2 cos 2 pi fc tau. Again, if I want to this is autocorrelation function. If I want to calculate the power spectral density, this is given by the Fourier transform. Fourier transform 4 means Fourier transform is 4 del f. So it will be of area, impulse of area 4 at 0, and again 2 impulses, one at fc, the other at minus fc, as we have seen in the previous case, AC square by 4 here, minus fc, AC square by 4. Now, if I have a DC signal, DC value present in the signal, here I am going to get an impulse of strength 4. means from the power spectral density I can get the DC value, that is if there is a impulse at or is at 0. So if there is an impulse at 0, the signal will have DC value. If there is no impulse means DC value is 0. Here impulse is not there, means here there is no DC. So here also you can calculate the power. If you want the power spectral power, total area gives the power. From this power spectral density also we can calculate the power. Here power spectral density area, one impulse is 4 plus AC square by 4 plus AC square by 4, AC square by 2. Here what is the power? DC means DC square plus AC square by 2. So from power spectral density we can calculate the power by calculating the area, and we came to a conclusion that if we have a DC, we must have an impulse at F is equal to 0 in our power spectral density. Now come to our question here. Here if you observe, there is no impulse at F is equal to 0, means DC is 0. So expectation of W of t will be 0, so that expectation of Y will be 0 here. So we came to a point, expectation of Y is equal to 0. So variance of Y is what now? Variance of Y simplifies to expectation of Y square. Expectation of Y square, which is nothing but mean square value. Mean square value, and we know that mean square value is nothing but the total power. Mean square value, if I want to calculate the variance, it is simple if you calculate the total power. Now total power, how to calculate? In random process we studied that total power can be calculated from power spectral density. Just now we have seen also. So area under power spectral density gives power. Now how to get the power? Now if you look at the expression, expectation of W of t is 0 as there is no impulse at F is equal to 0. So what happens here? Expectation of Y is equal to 0. We came to this point. Now if you substitute this value here, your variance of Y is simply expectation of Y square, which is nothing but mean square value. Mean square value, and we studied that mean square value gives the total power. So if you want to calculate the variance of Y, simply calculate the total power. And how to calculate the total power? And we know that from the power spectral density, if you can calculate the area, you will get the power. Just now we have seen. Now what I am doing is I am removing this. I don't need all this now. Right. Now suppose if you have a LTI system with input x of t, impulse response h of t, then your output is y of t, and we know that output y of t is given by simply the convolution of x of t with h of t, and the convolution expression is integral minus infinite to infinite x of tau h of t minus tau d tau. Now, and one more relation also we know, if you are passing a random process through a LTI system with impulse response h of t, Sy of f, output spectral density, is equal to input spectral density into magnitude of h of f whole square. So that I can get the spectral density, power spectral density, and I can calculate the area, so that I will get the power, which is nothing but mean square value. But observe here, if you look at our expression, Y is integral minus infinite to infinite phi of t into W of t dt, or I will interchange, better I will interchange, I will write like this, W of t into phi of t dt. Now if you look at these two expressions, they resemble the same. See here, independent variable is tau, whereas independent variable is t here. Now if you compare these two expressions, what is the difference here? Here in the impulse response, whenever we are calculating, we'll have a folding, which corresponds to this minus, and we'll have shifting by t also. Now this shifting by t will have exponential multiplication when it comes to the magnitude So exponential multiplication will not play a significant role. And coming to this reversal, now in convolution general we will take the reversal also. If you consider this reversal of h of t, that is h of minus t, h of t and h of t being the real signals, their spectrum is symmetrical. So h of f whole square will come. So here, so we can say that this shifting and that folding will not have any effect on this magnitude of h of f whole square. So for this one, I can write sy of f, comparing this one and this one, is nothing but sw of f into phi of f whole square. Now I got the relation. Again, if I output power spectral density I got. Now I can calculate the output power. How? Area. Area means integration. Integral minus infinite to infinite sy of f df is nothing but integral minus infinite to infinite sw of f into magnitude of h of phi of f whole square df. Now this being a constant value 3, now I can take it outside, integral minus infinite to infinite magnitude of phi of f whole square df. Now according to the Parseval's relation or Rayleigh's energy theorem, I can simplify this as this is nothing but the energy in the signal phi of t, magnitude of phi of t whole square dt. This is nothing but 3 times, find the energy in the signal phi of t. Now this is rectangle kind of thing. Now always remember, for rectangle pulse kind of thing, energy is given by a square b, where a is the amplitude, b is the width. Here a square is 1, width is how much here? 2 units. So which is nothing but 6. So area under power spectral density, that is power, that is mean square value is 6. So here just now we have seen that mean square value is nothing but variance. So your variance of y will be a value 6. This is your answer.